Go ahead.
Okay, so today I'm glad to present the results of our work that we just submit the preprint. This is the molecular learning dynamics work. So this is the outline of my today's talk. So we'll start with some introduction, then we will discuss how the molecular systems may be described with the classical mechanics, and how the equations of motions can be derived and how they can be generalized. And then we'll discuss the third part. We will discuss the physics learning duality, or how can we develop the alternative interpretation of physical equations of motion from as an emergent equations from the dynamics of the learning system of agents. And the fourth part, we will consider the agent loss function, how the loss function can be constructed in order to obtain the learning dynamics of an agents that will correspond to the some real physical system. And finally, I will show some numerical results that we have. So let's begin with the introduction. So the molecular dynamics is the very important and foundational task in various disciplines, from biophysics, material science, and others. And so the general molecular system can be described in the quantum mechanics framework. So if you have a system consists of nuclei of different atoms, they consist of nuclei and electrons, and in general you need to introduce the wave function as a function of q, which represent positions of all particles and electrons involved in the system. And the dynamics will be given by the Schrödinger, time-dependent Schrödinger equation number 1. Although it's correct description, but it's computationally kind of impossible, both numerical and analytical, to solve for relatively small but realistically large systems. So it's only analytically, it's only like for very simple cases, like an atom of hydrogen, just one atom, it can be solved, but for harder systems, for like collection of molecules, it's impossible. But there are certain approximations that allows to essentially simplify the analytics, the description, so to have some description that will be possible to solve on computers. And this is the approximations of density functional theory, of like Born-Oppenheimer approximation, where you can separate nuclei and electrons' degrees of freedom, and then at certain limit you can use only the description of classical mechanics, where you only have nuclei as particles, and the influence from electrons will be inside the potential energy function. And we will discuss it now. So it's description of molecular system that consists of nuclei. So let's denote their positions as Q. And then we can define the Lagrangian function with two parts. The first part is kinetic part, the second is the potential energy part, and then one can construct the action functional, and to obtain with variational principle, optimizing this action, one can obtain the equations of motion, which are also known as the second Newton law. Just like acceleration, you have the mass term here, and you have the minus gradient of the potential energy. Okay.
Yaroslav, I think you should also tell about this new notations that you're using, right?
You mean inside the function, right?
Yeah. I mean, it's very unconventional, right?
Yeah, I mean, some time ago when you present to us your paper about emergent field theories, I believe you had this already, but yeah. So this notation means that like kind of similar when we have like contraction of indices, lower and upper indices. If they are repeated, they are kind of contracted but if they are inside of the function, it just means that this function is really a function of many variables, and like all these Gijs are the variables inside this function. Yeah, and the contraction will be in the case when v is linear function of its arguments.
And the same for Lagrangian function, yeah. So you have now.
Yes, exactly here, yeah. It's just for the convenience, for simplicity, and really, personally, I like this notation. So it's
compact. It's
compact,
maybe considered a generalization of Einstein convention, right?
Exactly, yeah. Okay. Here we consider the particular example of how can the potential energy look like. So in case of two-body interactions, and now we consider different types of particles. You can have, for example, in water system, you have two types of atoms, like hydrogen and oxygen. And so in arbitrary systems, there will be capital A types of nuclei of particles, and so we can define the function AI of as an index. So given the index of a particle, it maps you to the space of the types of particles. And there is an inverse function that for a certain type gives you the set of all particles of this type. And then for the two-body interactions, again, we can introduce the potential energy, represent the potential energy as a sum of two particles interactions for all pairs. And it's convenient to group certain terms in this sum, so that you have this double summation, but in internal sum you have sum of interactions over particles of type A with the particles of type B. And the outer sum, external sum, it's sum over these types, different types. It's just rewritten this summation. Then we may be interested in getting the equations of motion, so that as previously we need to differentiate the potential energy, and so we perform this differentiation. And for a given particle k, it already has some certain type AK, and so one sum is actually, we don't need here sum over B, because one type already, you already set one type of a particle AK here. And so you write the following equation 6, where we can define the following quantity phi. It's convenient to define it in the following way of equation 7. So phi is invariance that encodes the interaction of a particle k with all particles of a type A, small a here. And so the force that is acting on a particle k represents as a sum over interactions with other types A, types of different types of other particles. And Yeah, so here phi is kind of a field that is useful quantity to define because it's kind of tells a particle k how it interacts with other particles through this field. And here the important comment here is that if we drop the first equality here and only consider the right one, so essentially if we don't have equation 7, if we only have somehow defined fields phi or invariants, it is kind of more general case because your invariance does not need to be defined as a sum. It might be a nonlinear, more complex function of distances to other particles, essentially. And another important comment here is that if you define your total potential energy, then your indices would be symmetrized there. So the invariant phi given by the equation 7 should be symmetric with respect to permutation of its indices. Okay, and this is the generalization to many particle interactions, meaning that we don't write here the total energy, but we from the very beginning write the invariants in this form. So we construct them as a sum over interactions of particle k with other particles of types b, a, and other types, that is here inside the dots. And the argument of this complex interaction, many-body interaction function, the argument would be the different geometric invariance that tells about geometric properties of interaction. So, for example, for 3-point interaction, you may consider 3 particles interacting, and one invariant could be the square of a corresponding triangle, or area of the triangle, for example. But there might be another quantities that tells you about about relative positions of the particles that are interacting. And then one can easily write down the equations of corresponding equations of motion for this many particle interaction case as well. And also here the kind of equation 10 is more general because phi does not need to be to satisfy equation 8. And then in this case there probably will be no Lagrangian for the whole system, and there does not need to be satisfied the third Newton law, for example. That will be the case of the system with the Lagrangian function with the potential energy function that is defined for the whole system. Okay, and this is another generalization, the nonlinear generalization, actually, so that if you have your invariance phi, you may actually consider a nonlinear function of them, not just here, just the sum of them, but you may consider a nonlinear function of your invariance, of your fields or invariance phi, and then the gradient of this function will give you the force or the acceleration. And in terms of two-body interactions, you will have two-body invariance here, which are the functions, arbitrary nonlinear functions of pairwise distances of particle k to the other particles I. Okay, For these equations, for equation 12, for example, there might be different interpretations. How is that can be possible? So first is the classical physics interpretation, meaning that there might be the effective Lagrangian for the whole system, so that if you construct the action, if you perform the variational principle and extremize this action, then you will obtain equations of motion 12. And this is completely classical interpretation. But for an arbitrary h, for an arbitrary phi, there might be no Lagrangian, actually, no potential energy. And so the useful other interpretation that will give you exactly the equation 12 is the learning interpretations when you consider your particles as an agents. And so this is my next slide is about, the next part of my talk. It's about this agent particle learning, how can we construct this interpretation of physical motion with, from the point of view of learning theory. So you may think of a particle K as an agent that is as a learning system, essentially, that performs the following steps. So first, it scans for the positions of other particles, other agents, and this first step might be considered as a boundary dynamics, so that the positions of other particles appear as the input layer of the corresponding neural network of this agent K. Then there is the second part, is the encoder part. This is how this input data is processed by the agent, and this is how these phi are constructed through this positions of other agents, and also this phi. This agent is mostly interested in how the invariants depend on its own position, qk. And the agent K actually treat his own position as a trainable variable this agent can change, actually can adjust. And how it can adjust it, it's the learning dynamics. And for this we need this third ingredient, this loss function, to be defined, so that once the particle obtain input data, then it process and obtain invariance, and then invariance, you may think of them as a kind of output of the encoder layer, and then you may define some loss function at this output. And this function kind of the quantities that the agent wants to minimize, and so it needs to perform the gradient descent. But before the gradient descent, there is this important fourth step. It's the averaging of the gradient of the loss function, which is also a very useful in machine learning approach when you not only consider the gradient of the loss function, but average it over your mini batches, kind of, or over the time here. And this is equation 14 is about. So you construct the quantity f, covariant quantity f, which is just the average, actually exponential average, and I will show you later how it looks like, but it is an average value of the gradient of the loss function. I mean minus gradient, because for the fifth step we need to move according to the gradient descent, and so it's useful to just put minus already inside your force, and then you will have this equation 15. It's fifth step, it's the gradient descent, actually, so that you adjust your trainable parameter, which is your position q, according to the average gradient of the loss function, where here tau over m is the learning rate. And for now, it is the first order kind of equation, and for the Newton's law we have the second order, and so we need some trick to get the second order equation. And so first let's consider how actually f is constructed. So essentially the equation 16 is probably more easy to understand, because here you have just the minus gradient of the loss function and averaged just exponentially with exponential window function. And this is, the equation 16 is actually equivalent to the equation 14. But your equation 14 just gives you the rule how you need to adjust your f dynamically. So that you don't need to collect or your gradients and then integrate them. You just can adjust them. But by adjusting your f according to equation 14, you will effectively get the exponential average. And so then if you differentiate actually the equation 15, this is the gradient descent. If you differentiate it once again in time, you will get the equation 17. This is the second order equation, and without f. So you just this way you can get rid of f essentially, and get the equation 17. And to get the Newton's law, you need to consider the limit of large tau. So large, if exponential parameter tau is large, or more precisely this term, the second order term, dominates over this first order term, you can vanish this first order derivative, and then you will you can also get rid of tau, and then you will effectively obtain the equations of motions 12 that we had before. So essentially the acceleration proportional to the minus gradient of some function, some scalar function, and in the learning case it's the loss function. And so here, and if for the loss function and this invariance, if there is a certain Lagrangian that will give you the same equations, then there will be the dynamics of the learning system will be equivalent to the dynamics of the corresponding classical system with a certain Lagrangian. But again, for arbitrary h, you may not have such a Lagrangian. And so this is the more general. Okay, and let's consider. Do you have a question, Vitaly? Or?
Yeah. So there is a separate loss function for each type of agent, each type of particle, right?
Yeah.
Each subcategory. Okay.
In general, yes. Okay, and here we will consider more specific example. How can we construct, how the invariants can look like, how we can construct them, how we can try to model some real system with this approach. So our invariants might be constructed as just the sum over all particles, meaning that we sum with interactions as a sum of this window functions or weight functions, Wm. They are some decaying functions, so that interaction with far away particles contribute less than interactions with closer particles. If the distance is shorter, then the value is larger. And this functions W might be like exponential functions, exponentially decaying functions as its argument. It can be Gaussian functions, power law functions, and exponential and Gaussian are more local. they are kind of so suppress the faraway contributions, severe kind of, and power law less restrictive, and they have some heavy tails, and may be relevant for the long range interactions. Okay, and then how the loss function may look like. In general, it will be the arbitrary nonlinear function of invariance, but we can consider for simplicity. For now, we considered just the square quadratic function of phi, and so we have this tensors A and B that are the parameters of H that can be trained, for example, or like chosen in a way that they give the realistic behavior of a particle of learning agents. And here the corresponding equations of motion represented in Formula 23. We just differentiate this H with respect to the particular Q, particular position of particle K. And then this acceleration is now constructed, consists through the invariance and the gradients of the invariance. And then we may from this point consider the supervised learning approach, where we start from collecting the data about some realistic system. We took the water simulation of 128 molecules performed in CP2K software with the density functional theory approach. And this data we use to obtain the correct accelerations, how they should look like as a functions of invariance. And then we can train for these parameters A and B tensors of our model of agents loss function in order to get the realistic accelerations or forces. And to do that, we choose these window functions weight functions as I propose, so exponential, Gaussian, and power law with the following parameters. And so we may then proceed with the kind of process of invariance or feature selection, meaning that we may drop some weight functions, that some invariants essentially that are not give you a better prediction of accelerations. And so this is how we train. We train in order to minimize the mean squared error loss function, meaning that we want our Q double dot of the learning particles being as close to the real AK nu as close as possible. And the AK nu, these values are the values from the data set, from the correct simulation of water. And this is how our loss function look like. And we minimize it with respect to tensors B and A. And the brackets represent the averaging over the whole data set that we have.
So basically there are two H's there. So the telegraphic H is how you search for the coefficient that determine the loss function of agents, which is the normal H, right?
Mm-hmm. Okay. Yeah, we train in order to minimize the calligraphic H, and normal H is a quadratic function of invariance.
So you're learning how agents learn. Learning how agents.
Yes, exactly. If within this kind of picture, when we look at particles as learning systems, as an agents, and so we try to figure out what is their loss function, actually, which they minimize by moving in a certain way. Okay, and this is how the procedure of invariant selection looks like. So basically, we start from all invariants, all these window functions, exponential Gaussian power law with different parameters, and then we starting from the right of this plot and removing invariants one by one in order to minimize the validation loss function, calligraphic loss value, meaning that some invariants might be irrelevant for the particle's movement, so they may lead to the overfitting, essentially.
They're either irrelevant or they have redundant information with other invariants, right?
Yeah. So, for example, if we only use few invariants, it's not sufficient to get correct accelerations, and then it drops and at some point reach some minimum value that correspond to approximately 30% error with respect to the CP2K simulation, correct simulation. The same for hydrogen. Okay, and this is when we choose the optimal hyperparameter, optimal sets of invariants, we train the models for A tensors and B, and here are the results of the simulation. Essentially, the blue line represent the, in this case it's kinetic energy I plot here. So from time 0 to 1000, it was the CP2K simulation performed. And you can notice from the beginning some sudden growth of kinetic energy in CP2K simulation. So this kind of corresponds probably to bad initial conditions, I believe. So, nevertheless, the system kind of gets to some equilibrium, I guess, after the 200 time steps. And so for the training of our models, we used the data from 200 time step and approximately to 800. It was the training data where we train. And then we can start our own simulation and look how well we are performing. And here we also used the thermostat for the simulational purposes in order for kinetic energy to be stable, to be conserved. And kinetic energy essentially correspond to the temperature also. And yeah, so in the long run, you may see that kind of the system behave more or less stable. These fluctuations are larger for the temperature, but that's about mostly about the thermostat parameters that probably might be chosen in a way that to suppress these fluctuations, but it's not very important. And so their simulation you may already see in the video, the YouTube here, how kinetic energy look like, and there are other quantities that we considered. For example, the distance from hydrogens to the respective oxygens.
Are you going to show us the video? Or?
I mean, probably not, because you have this in the Telegram group. So okay. I guess everyone already
well, since we will be posting videos. It to YouTube, maybe having a simulation would be nice to see. Maybe later, but
yeah. Okay, so one may consider different statistical quantities of the simulation, like this one, where we consider the values of the distance of hydrogens to respective oxygens within the molecule, and we can see that the average distance is kind of correspond great with the CP2K with correct simulation, and standard deviation is also similarly looking. So from this one can kind of derive the the bond length, which is about 1 angstrom for the water, and this is how this distance from hydrogen to oxygen evolves with time. So it's actually vibrates somehow. So there is an oscillation or like movement of hydrogens. So they kind of reach some maximum value of the distance. Then they attracts, they repulse, and so on. There is this oscillations, and then we can see that they looks kind of similarly for the learning simulation with the respective physics simulation, and then I also performed the Fourier transform essentially of this bond oscillations. This will exactly tell us at which frequencies there are these oscillations. This is kind of the vibrational spectrum of the system, of the molecule. And there is this peak at 3000. There is a certain peak that is present in both physics simulation and our learning simulation. Here I also we studied the dynamics of how this peak can drift with time. And so we can check and verify that in the long run, this peak is also pretty much stable around this value of 3000. So it does not drift much. Okay, and finally there is this results about the angle in the molecule. So in the physics simulation, the angle in a water molecule is about 105 because we already seen that there was a growth of kinetic energy, and so for the water at room temperature it would be lower, but still it's 105 kind of degrees. And for our simulation it's larger, but maybe not so much. But again, this is just the illustrational purposes of our approach of learning. So it kind of more or less works. For some quantities better, for some not so well. And this is also the standard deviation of the angle plotted here, the right picture. So the standard deviation, the fluctuations for the angle are also higher. Okay, this is it for today.
Thank you, Yaroslav.
If there are any questions, we'll be glad to answer.
I do have. So
Go ahead, Diego.
here's the thing. When I started reading it, I got in my head that this was a physical learning project, just like my speed system stuff. But it's not really, is it? It's more of a computational thing that you're using, that you can use to simulate molecular dynamics maybe more efficiently or something like that. Okay, so that reframing change helped me a lot to understand what's going on a little better, because I was very confused at some point, like how are we going to get molecules to obey these relations? Maybe you can get electromagnetic interaction or something like that. No, so this made to run on a computer, right?
Yeah, well, it's both, right, Diego? I think maybe I'll jump in and say so. Yeah, you can use this learning perspective to to do the faster simulations. And so I think whatever took 10 hours to do usual physics simulation, it took 20 seconds to do using this.
Yeah, in our runs, it was much computationally faster to run the learning simulation. Yeah.
Okay, so but there's still some
But that's
intention
only
of making a physical learning system.
yeah, but that's only one side of the story, right? So you can but now there's another, like, if this is correct, and if this is how molecules actually behave, if they're equivalent, if this is dual system, then you may ask the question, okay, can we actually maybe for more complex system, molecular systems, larger molecules, I don't know, chains of molecules, what's not, do the opposite? Can we like make use of this loss function, cleverly chosen loss function, and make it learn whatever we want it to learn? So can we actually do learning of the physical systems using this dual approach? So that's kind of a second other side of the coin, yeah. So learning helps you to do the physics simulation, but maybe then physics can also be useful. Physical system can be useful to actually doing the learning tasks, right? Yeah. Because after all, if those two descriptions are dual, you just use whatever is more useful for whatever problem you're trying to solve. Okay. Other questions, comments? There are no comments. Thank you, Yaroslav. And so, as I understand, this should appear on the archive tonight, but it's already
Yeah,
it's already in
hopefully.
the chat. It's already in the chat. All right, perfect. Thanks, everyone. Thanks.
Yeah.